Hello everyone, and welcome to AISC's live webinar, Design of Reinforcement for Steel Members, Part 2, presented today by Bo Dowswell. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce today's speaker, Bo Dowswell, PE and PhD, Principal at ARC International. Bo Dowswell has been in the steel industry since 1985, the first 9 years which he spent as a detailer. He is principal of ARC International, an engineering firm specializing in design and research solutions to complex problems in steel structures. He received a PhD in structural engineering for his research on gusset plates and is an adjunct professor at the University of Alabama at Birmingham. He is a registered professional engineer and has published several journal articles on steel connection design and beam stability. Bo is also a member of the AISC Committee on Manuals, as well as the AISC Committee on Industrial Buildings and Non-Building Structures. Very pleased to have Bo Dowswell here today. Thanks for being here, Bo. I'll hand things over to you.
Okay, thanks, Brent. Before we can get started on this part 2 that we're going to talk about today, let's do a quick summary of what we discussed in the part 1, which was a couple of months ago. If you missed that one, you can take a look at that link on the bottom of the screen there. And I believe if you go to that website link, you can download the video and the PowerPoint slides. I believe they're in PDF form on the AISC website. But in part 1, basically we talked about two different things. We talked about reinforced beam design and reinforced column design. And within those two items that we talked about the different reinforcement types, which reinforcement type is best to resist certain types of loads. And then we also talked about the effect of preload and partial length reinforcement on the strength and stability of the members. Now, one thing I wanted to go ahead and define what a preload is, because we're going to use that terminology in this presentation too. A preload is just a load that's on the beam or column at the time of reinforcement. It's on your structural member at the time when you add the reinforcement. You can't always remove 100% of the load that's on your structural member before you add reinforcement. In fact, a lot of the structures that I work on, industrial type structures, it's almost impossible to remove even a lot of the live load. So you end up with what I'm calling a preload on that beam that you have to account for when you reinforce the member. So today what we're going to do, we're just going to do anywhere from 5 to 15 minute presentations on several different topics that are really unrelated. They're things that we couldn't cover in the first part and things that we got questions on in the first part. And for example, like the composite beam example, they're just different things that we thought would be good, would fit into the second part. Now, the composite beam example is going to be a little bit longer than the 5 or 15 minutes. It's going to be about 25 minutes, and that'll be the last thing that we go over. So let's go ahead and get started with beam deflection. Now, I know that beam deflection is something that we really don't think about too much. You know, we build our finite element model and put the loads in, put the beam properties in, and at the end we check to see if the deflection is within a certain limit usually, or maybe it's the other way around. Maybe we check the deflection first and then the strength. But we really usually aren't too concerned with the background behind the calculations. But there's one problem with that when you're reinforcing beams. If you build your finite element model with reinforced properties and you have a preload on that beam, then you can get more deflection than you think you have, just looking at the finite element results. So let's take a look at that. Let's say that we have this preload on the beam, omega sub n times P, where omega sub n is just the portion of the total load that is going to be on the beam at the time of reinforcement. So we end up with a deflection delta sub n. So then we go in and reinforce that beam, and we've got this proportion of the load on there, omega sub r times P, and you get deflection delta sub r, which is for the loading and the deflection after the reinforcement has been added. So really using superposition, all we have to do is add those two together. So it seems easy enough, but the problem is that if we've built our finite element model using the total load on the structure, including the preload and the post-reinforcement load, and we've also built the finite element model with reinforced section properties, we really don't know either of these deltas, delta sub n or delta sub r. So what we can do, and I'll show you this equation, but really all I'm trying to do is show you that just to watch out for this. You know, not necessarily that you have to go in and calculate every beam based on this equation, but just make sure you're aware that the deflection may be more than you think it is. So the deflection, the total deflection is going to be delta sub n, which is the deflection you take out of your finite element model, times this term in the brackets, which is going to be greater than 1. Remember, our omega sub r and our omega sub n have to equal 1 because all they're doing is proportioning the load. What you'll do is just estimate how much load you have on there before reinforcement, and the remainder is going to be omega sub r. You multiply omega sub n times the moment of inertia ratio, I sub r over I sub n, which is the reinforced cross-section moment of inertia is I sub r. The non-reinforced moment of inertia is I sub n. Okay, so that kind of gives you an idea on how to account for the preload in the beam. But I do have this one last slide that I want to talk about on beam deflection. It's a completely separate topic. What if you have a partially reinforced beam, like I've got shown in the left-hand picture? Well, the easy way for me to do this is just separate that one member, that beam, into 3 elements, like I've got shown in what I'm calling the finite element model on the right-hand side there. And of course, you're going to use your reinforced section properties in the middle section there, and the non-reinforced section properties on the ends of the beams. Now, I probably should have taken the S off of properties here, section properties of built-up members, because we're only going to talk about one section property here, and that's going to be J. And J is going to be the torsional constant. And of course, you need it when you're doing a torsion calc, but you also need J when you're calculating lateral torsional buckling strength of your beams. So I'll show you my main concern here. I'm not so much worried about the equations again in this section, but I'm more concerned about just the philosophy behind this, and I'll show you why on the last couple of slides of this section. Let's look at individual behavior. There's 2 ways you can calculate J. The first one is individual behavior. And if you remember from way back in Strengths of Materials course, if you have torsion, the maximum shear stress, and we're talking about St. Benoit torsion here, not warping torsion, but your maximum shear stress on the cross-section is going to be on the outside edge, like I've got shown here. It goes around the outside edge of the Y-flange section. And because we're twisting independently, we treat the plate independently too. So the shear stress is going to go around the outside of that plate. Now on the other hand, let's say that we have a continuous weld between the plate and the wide flange member. So now we're going to take a look at integral behavior. And what happens is that the stresses, they kind of follow the same mechanics that I was just talking about. They go around the outside of the section, but once they get up here, it kind of goes around the combined section. So what you get is a bigger moment arm because of the maximum stress is here and here rather than in the flange here and here, and in the plate, of course, it's here and here. All right, so you get a much bigger J for the integral behavior. Now these next 4 slides, really I'm just going to go through pretty fast. When you have individual behavior, you just add J of the wide flange to J of the reinforcement. In this case, it's a plate. Same thing if you have 2 plates, just sum the 3 J's. And then we get into integral behavior, and we need to account for the extra stiffness that you get. So we add this term here to the 2 J's, and what that accounts for is this cross-hatched section down here, and gives you a good bit more strength and stiffness for torsion. And there's the equation if you have 2 plates, one on top and one on bottom. But here's one of the main things I wanted to talk about here, is if you have stitch welds, or as they're known in the AIC specification, intermittent welds, then you have an area that's at the welds here where you're probably going to get close to the integral behavior. And then in between the welds, over this distance C here, you're going to have the independent behavior. So how do you calculate that? Well, if you go to most commercial software packages, you know, there's several, I call them shape builder software packages, where you kind of just graphically add in whatever shapes you have for a built-up cross-section, and it calculates all of the properties for you. And I'm very familiar with 2 of these software packages, and I can say that one is really bad and gives you wrong values, and one is extremely good. And both of them are pretty easy to use. It's just that the numbers that you get are not accurate out of one. So your software packages are going to calculate J sub I, which is integral behavior. Now, if you have stitch welds, that's going to be unconservative for your lateral torsional buckling and your torsion calculations. So what you can do, if you just want to have an easy, quick solution, you can just use J sub S, which of course is the independent behavior, where you just add the J's together. So that's simple enough. But a lot of times this can be extremely conservative, sometimes by a factor of 3 or so on a cross section, maybe even higher. So what we don't really have time to go over it, but this reference, the Chang and Johnson, it's over half a century old now. But what they did is they did testing on I believe they had riveted plate girders, and between the rivets, they wanted a way to calculate J effective for these riveted plate girders that were built up out of plates and angles and you know, the way they did it back in the 50s. But what we can do is we can use those same equations for stitch welded members. So take a look at that reference if you're interested. I have a list of references. I believe there's only 3 this time at the end of the presentation. Okay, our next unrelated topic, we're going to move on to weld design. Now I've got 2 good topics in weld design. The first one is going to talk about stitch welds. And one thing about stitch welds, you're obviously going to get a lower cost because you have less welding. You have a little bit of cost in the measurement of these, but the cost of the welding saved is going to far outweigh the cost of the measurement. One of the things I like about the stitch welding is that you get a lot less shrinkage distortion. And if you were in on the part 1 of this webinar, you'll realize from that plot that I had on the column curve that the out of straightness of your member that can be caused by the weld shrinkage distortion causes a huge reduction in strength to your columns. Now, the one negative for intermittent welds is greater corrosion potential, but we'll talk about that a little bit later about how the rules in the AISC specification will act to cut that down. And also, this usually is not a problem, assuming that you follow the AISC rules that I'm going to show you, and you have a good coating system. So in Chapter J, there are a couple of rules that require you to have a certain length of stitch weld. In other words, the actual length of the weld has to be at least 4 times the weld size. It also has to be at least 1.5 inches. And the reason for that is because it just allows you to get a good weld. You know, if you've ever used a stick welding machine, I mean, for somebody like me that is just does it kind of as a hobby, it's hard to get those stick weld machines started. You know, it takes me probably 1 inch just to get the weld going good. So, of course, the guys that do it all the time in the shops and the fields are a good bit better at it. But and I understand the MIG and the flux core welding machines are a lot easier to get started too. Okay, so now let's look at section D4, which is tension members, and J3.5, which I'll show you on the next slide, the AISC rules, but I want to explain why they're in there. They're in there to ensure close fit up of the bang surface, and if your structure is exposed to the weather, they're in there to cause a small enough gap where you can't, or where it's not probable that you'll have corrosion between the bang surfaces. And I've got a picture here that shows what happens where corrosion got in between the double angles. There were no stitch plates here. There were just 2 angles back to back. And the corrosion got in there. I believe that's probably coal dust, which of course lets the moisture stay in there longer and causes more corrosion. And then eventually the corrosion expands, and you can see the weld that cracked there due to the expansion of the corrosion. Now, it's not the exact same case that we have, but it's a similar thing. We can get our welds can crack due to corrosion if we don't follow the proper rules. And here's what the AISC specification says about it. The maximum P, where P is the distance between center of welds. The maximum P is 24 times the thickness of the thinner part joined, with a maximum number of 12 inches. For unpainted weathering steel, it's a little bit more restrictive, but usually I'm not involved with unpainted weathering steel. Okay, now let's move on to the next topic in welds, and that's going to be welding to loaded members. We briefly touched on this just kind of as a warning in part 1, but I want to expand on it here. This is kind of an interesting topic, and what happens is that your welding is obviously going to cause heat input into the base metal, and as the base metal gets hotter, as the temperature goes up, the material properties go down. and that applies to the modulus elasticity and the ultimate strength and the yield strength. So the first thing I'm going to do is give you some general recommendations, and then we're going to move on to some detailed analysis of this. Okay, first of all, we want less heat input, which means we can use small diameter electrodes and low welding current, stringer beads instead of weave beads. Now, if you look at it, I recommend that you, if you're concerned about this, welding to a loaded member, that you get the WPS, the welding procedure specification from the erector, and take a look at it to see exactly what they're going to do. Because you don't want them with a high heat input welding process that's going to cause your too much heat input on your beam or column. So stringer beads. Usually, if you look at a WPS, you're going to say stringer or weave beads. It's going to have an option there. So you may want to just go with stringer beads, which is exactly what it sounds like. It's just a straight line. It's what we think of when we think of welding. It's just welding along a straight line. Now, weave beads, on the other hand, it's just like it says, it weaves and it stays in that one area for longer, which adds more heat input in that area. So just kind of use judgment on things like this. And then, of course, we've already talked about the stitch welding. Now, these three items, we're continuing with general recommendations. This slide shows three related items, and it's all related to the inner pass temperature. If you're welding thin material, ½ inch or so, you may want to set your maximum inner pass temperature to 300 degrees Fahrenheit. Now, this is all shown on the WPS too. Generally, it's going to give you, the ones I've seen say 600 degrees Fahrenheit max inner pass temperature. Now, the reason I say where appropriate on that bullet point is because if you're welding two 4-inch thick plates together, your minimum preheat is going to be 300. So you can't very well have a maximum inner pass temperature of 300 also. You're going to have to go much higher than that. So you may just want to talk with the erector about some things like this before they actually do the work. And the next two items, just allow weld passes to cool before you start the next pass if you have multiple pass welds. And you can obtain the same objective by using this inner pass temperature of 300. And then the last one here, temperature crayons or other suitable means to monitor the temperature of the base metal. They should really be doing that anyway to get the maximum, to measure the maximum inner pass temperatures. The temperature crayon is exactly what it says. I'm not even sure if they're actually using this technology anymore, but you just mark the crayon with different colors, and if that crayon melts, then the temperature that crayon is meant to measure, if it melts, then it's above that temperature. So let's look at some of the more in-depth stuff on this for the next few slides, and it'll give you a good handle on how you can handle this. Let's say that we have a plate in the plane of the screen, and we're going to run a weld bead in the negative X direction, and we're moving from here all along this X line, and at this point in time that this plot was made, our weld bead is at this point, is at X equals 0. And what we have plotted is the temperature field in that plate. And you can see what happens. If you move away in the Y direction, perpendicular to the weld up here, that is roughly, for this heat input that this was plotted at, it's roughly 1½ inches. And it's to scale, so this dimension in the X direction may be 5 or 6 inches over here. So what we end up with is the different temperature lines, 600 degrees, 800, 1100, and then 1600 degrees Fahrenheit is what these temperature lines are. So what we're going to do is cut a section normal to arc travel, like I've got shown here, and then we're going to plot the temperature field. All right, so let's take a look at that. Here's our bead at 0, 0. It's coming in and out of the screen, and then we have on the horizontal axis we have the distance from the center of weld. On the vertical axis we plotted the temperature. And this is for a worst case. I've selected about 4 or 5 different sections along and cut plans, and this is going to be the worst case along that length of weld. So you can see it gets really hot up here. Actually, it's probably even hotter than that, but 1600 is enough for what we need. And by the time it goes fairly linearly, and by the time it gets over here at about 1.5 or 2 inches, the temperature is negligible over here. You know, it's 300 or 200 degrees Fahrenheit, which is not going to cause much of a reduction in strength. So what we can do next is look at a very similar plot on the next slide, but this time we're going to plot the modified yield strength. And what I have on the horizontal is the same as before. It's the distance from center of weld. But on the vertical, I'm plotting this alpha, where alpha is defined by this equation. This alpha times the specified minimum yield strength, 36 KSI or 50 or whatever the material is. So you multiply alpha times F sub y, and you get the yield strength at this temperature that I showed you on the last slide. So the higher the temperature, the lower the yield strength is. So alpha is 0 down here up until we get to around 0.3 inches or so. And then it goes up roughly linearly. And then by the time we get to 1 3/4 or 2 inches way up here, alpha is going to be 1. So it means we're not really affected by the heat due to that weld. Now, one thing I want to point out on these last 2, don't use this for anything specific. This is just for just an example that I made with certain welding parameters. In fact, I think it was made with heat input of 25 kilojoules per inch. And a lot of the flux core processes, you know, it can get to around 85, I believe, or 90 even, close to 90 kilojoules per inch, which would make this, it would move out in this direction. So it would make our non-effective, our area affected by the heat larger. So what I'm going to do with this curve is, if you plot the area above the curve, that gives you an effective and inactive area that you need to take that chunk out of your cross section. And here's what the numbers came out to be. For stick welding, these values are conservative. For stick welding, it'll be 1 inch in all directions, your W sub y. And always go from the opposite side of the element that you're welding, like the top flange of the beam here is where I measure my W sub y, or this side of the plate if you're going in this direction. So use W sub y in all directions of 1 inch and take that chunk out of your beam or column, whatever member you're welding to. Now for flux core, it's a higher heat input process, so I'm saying a conservative value for flux core, self-shielded flux core welding, is going to be 2 inches. All right, so what you do is you just take this chunk out, and if it's a beam, you calculate your bending strength based on the non-cross-hatched section. Now for me, personally, I just use the section modulus. I don't use the plastic modulus, and the reason is because I don't want to, when this weld cools, I don't want there to be a kink in my beam where that beam has gone into the plastic range. Take a look at that reference if you want a more accurate solution. In fact, all these numbers are based on that reference that's in the back of the presentation. It's a lot more rigorous solution. It may take a while just to get in, and you'll need the WPS to calculate the heat input and some things like that, some ARP efficiencies, travel speeds. So it gets pretty in-depth. Now another calculation I did is what happens when you weld across the flange. You know, I know that there's a lot of talk about you can't weld across the flange. I never really could figure out if it was welding across loaded members or if it was something to prevent fatigue or something like that. So I never really got to the bottom of why that rule of thumb was out there. But this might have have something to do with it. So a conservative estimate. Don't forget this is conservative. You know, make sure that you know, this is not the final calculation if it doesn't work. The conservative estimate is just knock out the whole bottom flange, the whole flange you're welding to if you're welding across the flange. In other words, you're welding perpendicular to stress flow. Just knock out the whole flange plus part of the web defined by W sub y from the last slide, either 1 inch or 2 inches above the top of the bottom flange. Now, I would, if you're doing something like this, make sure you go to that reference and check it out. Now, once again, I use section modulus on this, so it's going to give you a strength that maybe is 20% of what the full beam strength is. But remember, that doesn't mean that you can't do this. It just means that you're going to have a smaller load because your preload is not going to be equal to the total load on the beam. Hopefully we'll remove some of the load before we weld it. So we're going to have a smaller load applied, hopefully, and then you can locate these plates that are transverse to the stress. Hopefully we can locate these at a location along the length of the beam where there's not, you know, where the moment is much smaller. And actually I've done this method. I just knocked out the whole flange every time I've done this, and my plates are located so far from the maximum moment that it's worked every time for me. I haven't had to go in and do the more in-depth calculation. Okay, Brent, I think this is a good stopping point for questions.
Okay, if there's any questions out there, we'll be happy to address a couple of those right now. At this point, I'd say let's keep going, Bo, and we'll catch up with questions towards the end.
Okay. All right, that sounds good. Okay, let's move on to I've called this additional topics for built-up columns. And the reason I call it that is because we had several questions on the built-up column designs from part 1. And I wanted to incorporate at least the most asked question here. So what we're going to do is we're going to talk about how you calculate the weld strength for a built-up cross-section. You know, we talked just a little bit about this for beams in part 1, where we had the VQ over I for the shear flow and then the MQ over I for the anchor force. But the problem is how do you calculate those loads for a built-up column? Now, before we get into that shear flow stuff, which is what the questions were about, don't forget this part. You know, this is the part that I think is the simplest. But once you get into the shear flow calculations that I'll show you in a minute, we may kind of forget this part. At the theoretical cutoff point, at the end of your reinforcement, you have to develop whatever load is in that reinforcement through the weld to get it into the original member. Let's say our reinforcement cuts off short of the top of the column like I've got shown, and maybe our theoretical cutoff point is at this point. So your load that's this stress, whatever proportion of the load that is in your plate, has to be developed over this length, which is the development length. Okay, so really just to kind of to remind you to do that, I've just set up this simple proportion based on equal stress throughout the cross-section. The load in each plate is simply going to be the required load, the applied load of the column. P, that should probably be P sub R for required load on the column, times the ratio A sub P over A sub R, where A sub P is the area of the plate and A sub R is the total area of the reinforced cross-section. Okay, so now that that's over with, let's get into the part that we really want to know about, the shear flow. All right, this is the same slide that we had from part 1 where we talked about shear flow and beams. That's why I've got a beam over here instead of a column. All right, our shear flow is going to be dq over I, or B sub R for the required shear, times Q divided by I sub Rx, which is the moment of inertia of the reinforced cross-section about the x-axis. So really, for beams, all we need to really do is calculate Q, and we know the rest pretty much. Q is just the area of the plate times Y, which is the distance from the centroid of the plate to the centroid of the built-up member. All right, now the problem that you've probably already thought about is, for beams, we know what V sub R is. For columns, we don't. Okay, we've got a similar equation for our anchor force. The anchor force is simply, the shear flow is what happens between theoretical cutoff points over this distance, L sub RT. The anchor force has to be developed over the anchor distance, or the development length, D sub RT. So F sub A has to be developed over D sub RT, but it's MQ over I, where Q and I are the same as we had before, but M sub RC is the moment at the theoretical cutoff point. And once again, how do we find that? We don't know what M sub RC is in a column. Well, I'd mentioned one of the papers in the last presentation that you can look at. It was even in the references. But really, this is an easier way to do it. And it's kind of gives you a good procedure on how to calculate the shear in the moment at the theoretical cutoff location. And what I did is I stole some information from the direct analysis method. You know, they've got all the notional loads, and for the method that's spelled out in the specification, you apply your notional load to account for any initial out of straightness or out of plumbness of the frame. And that's what we're going to do here. The goal is to apply a notional load that gives you the same moment within your column as the initial out of straightness. So what we're going to do, P times delta sub O, where delta sub O is defined by the Code of Standard Practice as a maximum of L over 1,000. So P sub R, the load in the column, times delta sub O gives us a moment. To get an equivalent moment, we can apply a uniform notional load equal to WL squared over 8 over the full length of the column. And what we get, just set those two equal to each other, we end up with this notional load. A uniform notional load of W sub N equals the required load on the column, P sub R, over 125 L. All right, so that's how we're going to get our shear and moment at the theoretical cutoff point. Now, one thing I will mention is that the direct analysis method spelled out in the specification uses point loads, concentrated loads instead of a uniform load like I've got shown here. The reason I use a uniform load is because it gives us really what the direct analysis method is looking for, is to get an equivalent, or is to get the same moment. All right, so we've done that with this uniform load, but in our case, we want to get a moment at some point other than the location of maximum moment. So if we want to do that, we have to simulate what the buckled shape of the column is. And the buckled shape of a column is really similar to the deflection of a beam with a uniform load on it. All right, so you get roughly the same shape. So that's why I'm using a uniform load instead of a point load. One other trick is either you apply it in both directions, or in this case where you have flange plates, you would apply it in the direction that's going to give you a shear flow, which is, now I've changed it to W sub Y to indicate that it's a Y direction load. So for an axially loaded column with no loads within the length, no transverse loads causing bending other than the notional load, we end up with calculating our M sub C at the theoretical cutoff points, and the same thing for V sub R, the same thing for the shear flow on the column. It's going to be calculated at the theoretical cutoff point. Now that's not necessarily true if you have other loads on there, so just watch out for that and take your maximums along the length of the column. So we take a look at table 3-23, of course, and get the moment as a function of x and the shear as a function of x. But now you may think, well, all right, that was fairly easy. Now I've got my moment and my shear, but the moment has to be amplified. There's going to, when that column buckles, it's going to put a second order effect in there that we need to account for. Sometimes that second order effect can, it's going to be maybe 1.3, or it may be 2.3 or more. So we need to account for that. And the way we're going to do it is either with second order analysis. If you do this on a second order analysis using, most of the software does this now, so you can build your column out of several elements. Usually I break my column into 10 elements just for convenience. Or if you still like the hand methods, you can go to Specs Appendix 8, Section 8.2, and do the amplified first order analysis, which is the traditional amplification method that we're used to seeing. Your first order moment times B1 gives you your second order moment. So B1 is going to give us C sub M, which is going to be 1 in this case, times divided by 1 minus alpha, where alpha is 1 for LRFD, 1.6 for ASD, times P sub R, which is the required load on the column, and divided by P sub E1, which is the elastic critical buckling load of your column. And to get that value, you can use a stepped column approach like we talked about in part 1 of this webinar. So now that we've got M sub RC, we can calculate F sub A, the anchor force, the same way we did for beams. And this is just what we talked about on the first slide in this section, the force that needs to be transferred from the reinforcement to the column. And we need to add those two together. It's going to add on one side of the column and subtract on the other side. Now, I will say this. F sub P is probably, for almost every case you have out there, F sub P is going to be at least, I would say, 90% of F sub R. In other words, F sub A is usually pretty small. So what we have to do is develop F sub R over this distance, just like we would for beams. And the shear force per unit length based on V that we've calculated based on our notional load has to be developed over this L sub RT. Now I will say once again that the shear flow on a column due to that notional load is a small proportion of the axial load in the column. So unless you have a pretty big load on your column, you'll be able to get by with stitch welds over that distance L sub RT. Now this is kind of a topic that's really important, and one reason is because everything is not spelled out for you in the specification. You have to kind of do a little bit of engineering judgment and some calculations on your own for some of this. And what I'm talking about here for this flexural plate buckling is buckling, if you have stitch welds on a member, I'm talking about buckling between the stitch welds. So before we get to the flexural buckling, let's do a review of local buckling on these next two slides. And the reason we're going to do this is because they're kind of interrelated, and I'll show you in just a minute how they're related to one another. So for columns, just take a look in the specification, table B4.1A case 7, and all we really need to do to make sure we don't have to calculate any local buckling is make sure that lambda, which is B over T, is less than lambda sub R. And B is, like I've got shown here, it's basically the distance between welds. In this case, it's the plate width. In this case, it's the flange width. So there's our lambda sub R, 1.4 times square root of E over S sub Y. So that should be a review from senior level steel design course. So now let's move on to beams. We have a similar thing where we've got our B over T ratio is lambda, but this time we have lambda sub R and lambda sub P. And of course, lambda sub R tells us when we're going to be either non-compact or slender, and lambda sub P is the cutoff between non-compact or compact. So if we have a beam that we want to go into the plastic range, it has to be less than lambda sub P. And you can see that the 1.12 is a good bit smaller than the 1.4. So here's what I'm talking about between the flexural buckling and the local buckling. Local buckling, of course, is the traditional failure mode like this, and I've got this kind of on purpose. I put really small welds, and this is going to buckle kind of in a half sine wave like I've got shown, assuming that there's no restraint at these ends at the weld locations here. And the reason I did that is because that's what those particular equations that I just showed you are based on. It's based on pinned or simply supported plate edges. Now, that's not true for all of the local buckling equations in the spec, but for those I just showed you, it is. So now let's talk about flexural buckling. Now this is the length. This is on the length of the beam this time, looking at the web, or it could be a column turned sideways. This is the flange, and then you can see our plate buckles between the stitch welds that I've got shown here and here. So we need to prevent that. And everything I'm going to talk about is how to make sure that flexural buckling doesn't control the design over local buckling. Okay, first off, let's see what's in the specification. E6.2, which is for column design. For non-staggered stitch welds, let's take a look up here at the picture. I've got non-staggered stitch welds. One here and one here means non-staggered. There's some verbiage in section E6.2, and I just made an equation here out of the verbiage. So our maximum P, which is shown here, that's the distance between the center of the stitch welds. It's 0.75 times the plate thickness times the square root of E over S sub Y. And that can be a maximum of 12 inches. So this prevents this is a way to make sure that your flexural buckling of the plate between stitch welds does not occur before local buckling. So if you check this, you've just made sure that local buckling controls the design, and if you check local buckling, then obviously you've taken care of that. So let's move on. What happens if you put staggered stitch welds? It's a little bit more trouble maybe to measure it all out, and I'm not going to get any great artwork awards for this picture. I tried to freehand a buckle shape of what happens. You know, you've got your stitch welds once here, and then you stagger the next one over like I've got shown here. So this buckle shape is now going to be more of a local buckle in that plate rather than a flexural buckle, which is kind of a column type buckling. So due to that change in buckle shape, I guess for the professors out there, it absorbs, it creates more work, more energy to cause that buckle. Therefore, the AISC specification accounts for that. So you get a 50% increase in P max, 1.12 versus 0.75, and you get 18 versus 12. Okay, so there is a benefit to the staggered welds. Okay, now let's take a look at this a little bit more in depth, because everything we've just talked about, those last three slides, talked about what happens in section E, which is for columns. Now there's nothing in chapter F for beams in AISC specification. So what we can do is take a look at this reference. It's another one of those that's over half a century old, but it's a good one. They did testing and a theoretical analysis to determine a C over B critical ratio, where C is, instead of P, like AISC spec uses, now we're going to use C, which is the clear distance between the welds from here to here. So they found, and here's B, is traditional B for local buckling calculations, just the plate width perpendicular to the load. So what they found on these critical C over B ratios, it's all meant to give you a ratio that when you're below that, local buckling controls the design over this flexural buckling. And here are two of the values they got. C over B critical equals 0.5 for stiffened elements. In other words, I have a weld here and a weld here, so that's going to be a stiffened element. Unstiffened elements, C over B critical is 1.4, so that's going to be similar to this picture I've got here. So let's see what we can do for plates welded with stitch welds to beam compression flange. And we're going to use the C over B critical of 0.5, like I just showed you straight out of the paper. And then we're going to go back to local buckling. This is the equation I showed you earlier for lambda sub r for local buckling. And we're going to combine those two equations to give us our critical clearance dimensions. Remember, C is the spacing between the stitch welds. So this is C sub r. So that's our limiting, our maximum C dimension we can have for this situation. And here it is, 0.7 times the thickness times the square root of E over S sub y. Now you'll notice that that's really similar to what AISC had in their column section, which is 0.75 times T times square root of E over S sub y. So we know we're on the right track, but so let's take it a step further here. You know, we've got our lambda sub r for beams, but also remember, if we want that beam to be able to go into the plastic range, we have to check it out for lambda sub P too. So let's do our combination of lambda sub P plus that critical ratio of 0.5, and we end up with this equation. It's a lot less than the 0.7 or the 0.75. We end up with 0.56 P times the square root of E over S sub y. So that's one thing we need to watch out for. Make sure that that you're, for beams, beam compression flanges, that you take a look at this C sub P value. Now another way we can use that old research that I referenced. Remember, we also talked about this critical ratio, C over B critical is 1.4 for unstiffened elements. All right, so that might be this picture up here, where we have a free edge of the plate and one edge is welded. Now what we can do there is just go through the same process that I had before and come up with this C sub r as 1.4 times T times lambda sub r, where lambda sub r is going to be spread out of table B 4.1a or 4.1b. And the same thing for C sub P. If you want this, say this is a beam, and you want it to go into the plastic range, well, just use C sub P, is what I've called it, for plastic, as 1.4 times T times lambda sub P. Now let's go back. Now that's obviously if you want to stitch weld this member. You know, obviously, you know, you don't need to check this. If you don't stitch weld this plate to the web, or stitch weld this ear plate, or whatever we called it last time, to the column flange. Okay, Brent, I think we're at the composite beam example, so this is a good point to stop and take some questions.
Okay, we've got a couple questions here. Let me go back to slide 50. You're looking at weld design for columns. The question is this: how do you determine where that theoretical cutoff point is that you're showing on your diagram here for columns?
Okay, this is going to be something that's selected as part of the design process, and it's something that we go over in detail once we get to the composite beam example. Basically, what you do is you kind of, it would be similar to the way you would design a beam or a column, or at least the way a lot of people do. You know, you look at the load and you know, you say, well, I need a 1490 for that load and that length of column. Well, it's kind of a similar thing. You just select a theoretical cutoff point that you think is economical and that will be good for your load. And if it's not right, you just have to iterate to find it, which is what I had to do in the composite beam example, is do a couple of iterations on that.
Okay, and then I'm going to move back to previous section on welding to loaded members. The question is, I've got slide 40 up there. So talking about the ineffective area as it relates to where the hot weld is. So the question is, if you're welding along the length of the beam, then is the entire length of the weld part of the ineffective area?
No, but you would have to take the worst case. In other words, if you're welding along the entire length of the beam, you're going to have a maximum moment within that beam that is there at the time of welding. So you would take this chunk out at the point of maximum moment. Or I've never had this controlled, but you know, the maximum shear could also control too. So you may have to check two sections. If you take, you know, if that W sub Y takes out a little bit of the web for the shear strength too.
Okay. And then how long does it take for a weld to cool, typically? Oh,
that's a good question. I think we could get an idea by looking back at the plot. This may kind of tell us a little bit about that. Back at slide 37, because what happens as you're moving along in the negative X direction, you see this isn't going to answer the question, but you can see what happens. You know, when you're over here, you've got weld that kind of builds up, and as you're moving along, you know, let's say we're going to talk about at this cross section. The weld before adds heat at this cross section, and then when you're at the cross section, it obviously adds a lot of heat along that cross section. And then when you're ahead of that with your arc travel, it also adds heat back here. So it kind of builds up to a maximum, and then it falls down. But to answer your question, you know, I don't know. I don't know the answer to the question, but I can tell you that it depends on the distance from the weld. And, you know, if you're a foot from the weld, you know, it'll be cool to the touch. In a lot of cases, it depends on the heat input. For stick welds, like I do as a hobby, you know, you can touch it a foot away, you know, just a few seconds after or while you're welding, basically. But if you're 3 inches from the weld, then which is, I believe, roughly where the inner pass temperature should be measured, if I remember right. It's somewhere in that range anyway. It's going to take a good bit longer. I would say before you could touch it, I would say a couple of minutes at least, that far away, 3 inches away.
Okay. All right. I'll take us back up to the design example, and you can keep on going from here.
Okay, sounds good. All right, this design example, the composite beam example that we're going to go over here, it turned out kind of to be way more than I initially had planned on. So what I'm going to do, I wanted to make sure you had all the details in your handouts, but we're going to have to just hit the high points when we get through this, because if I remember right, it's somewhere, I don't know, 50 or 60 slides that we need to cover in 25 minutes here. And there's no reason to do that because, you know, I don't really deal with composite beams that much, and there are a lot more qualified people to talk about composite beams. So I'll concentrate on the reinforcement part of it, and you'll have the notes there that you can refer to later on the other parts. So what I did, I took one of the design examples that you can download for free on the AISC website. I took example I.1, and I said, well, let's use this example that initially had 100 PSF live load on it. Let's add 40 PSF to the live load. So the owner has come to you and said, I want to add 40 PSF live load to this beam. What do we need to do? And here's the plan view, straight off the example. And we're going to be working with this W21 at 50 beam. It's got 46 studs on it. They're symmetrical, so 23 on each side of the center line of the beam, which is also the point of maximum moment. And our tributary width is 10 feet. So let's take a look at this section AA through the beam and see what the decking looks like. We've got a 3-inch deep deck and a total 7.5-inch slab, so you've got 4.5 inches of concrete above the ribs of the decking. So this is straight out of the example problem, the original example problem. We have the stud layout showing that we have 23 studs on each half of the beam, but 2 are doubled up. We couldn't quite fit enough studs in there, so we added 2 at the end. So they're going to have a little bit less strength than the other 21 studs. So we've added 40 PSF to the original live load of 100. And I took these 2 values straight from the calculations in the example. We're going to need to know the available flexural strength of the beam, which is 769 kip feet. I took that value straight out of the example. The lower bound moment of inertia is 2,520 inches to the 4th, straight out of the example problem. So we're dealing with concrete strength, F prime sub C of 4,000 psi. And straight out of the example again, I've taken the dead load of 0.9 kips per foot. That accounts for the decking, self-weight of the beam and the concrete. So we'll end up with 50 KSI steel, and I'll go through this really quick. I've just added an estimated weight of 20 pounds per foot. I just kind of said, well, let's use 20 pounds per foot. Add that to the initial dead load, the dead load that's on the beam now, and we get 0.92 kips per foot as a uniform dead load along the length of the beam. Our live load is 1.4 kips per foot because we have a 10-foot tributary width. So we end up with a factored load, 1.2 times dead plus 1.6 live, of 3.34 kips per foot. And we calculate the moment based on WL squared over 8, 845 kip feet. So we know that our existing beam is only worth 769, so we're about 10% over. Additionally, we're over a little bit on the deflection too. So we're going to go ahead and add some reinforcement. So when we select our reinforcement, we need to make sure we know a few basic rules of thumb here. As we know from strengths of materials, the farther you place your reinforcement from the neutral axis, the more efficient it's going to be. And we know that partial length reinforcement is more economical than full length reinforcement. So we're going to try and do partial length reinforcement, especially because this beam is 45 feet long. This is kind of a review thing. Basically, the overhead welds are obviously, they're not impossible to do. They're just a lot less productive. They're 25% roughly as productive as a horizontal weld. So we're going to try and do horizontal welding if we can. One other thing to mention here is that make sure you've got an adequate shelf dimension. The shelf dimension is just the distance from the horizontal distance from the edge over to the free edge of the plate. And you need to provide enough there so you can get a fillet weld on there. Usually I'll use, say, a ½ inch of shelf dimension if I'm using a 3/16 fillet weld. Maybe if I think that something may have a chance to be out of tolerance, or if I'm using really long reinforcement or something like that, I may bump that up a little bit. Now, just to make the problem a little bit harder, I said, let's say that for some reason we can't weld to the bottom of the bottom flange, whether it's headroom or whether there are obstructions on the bottom flange. Something is going to limit us to adding reinforcement like I've got shown here would be a good location. So we're not welding on the bottom flange. Let's put an angle on each side of the web like I've got shown. And I'm going to start off with a 2.5 by 2.5 by 3/8 on each side. And just to make things more interesting, I said let's use 836 because we're going to combine with the beam, which is 50. I wanted to make sure we knew how to do that. The reason I chose 2.5 for the horizontal dimension is so that I could get a good weld, so that I could get a good shelf between this leg of the angle and the edge of the tip of the beam flange. So I went ahead and did this, even though it's really not going to make much of a difference. Go ahead and recalculate your moment. I think I took 1 kip feet. I think it changed from 845 to 844 based on the actual weight of reinforcement instead of the estimated weight. So now we can start getting into the actual calculations on the cross section. But before we do that, what we want to do is use the plastic strength of the cross section. But to be able to use the plastic strength, we need to make sure that our web can handle it without buckling. And the way we would check that is to make sure that the slenderness, the lambda of this web is less than lambda sub p. Now, the example problem does this same calculation, so I won't go into too much detail here other than just say that it worked. And if, I think in the commentary of the specification, it even says that all rolled wide flange members with 50 KSI or less will work for the web compactness criteria. So that means that we can use the plastic stress distribution. So let's take a look at what we need to do. The first thing we're going to do is calculate the concrete strength, and then next up is going to be the steel strength. But we're getting this 1840 kips. It's the area of the concrete times 0.85 F prime sub C. All right, but if you're used to doing composite design, which I'm not, if you are, you probably could tell immediately this is going to be a partially composite problem, which means that the studs are going to control the design. All right, so let's move on to the steel strength. It's going to be 860 kips. Notice that I included 50 KSI for the cross-section of the Y flange member and 2 times 36 KSI for the angle. All right, but this is not going to control either. What is going to control it are the studs. Remember, we have 2 at the end there, so they're going to be worth only 14.6, and the rest are going to be worth 17.2 kips per anchor. So let's add everything up and get 390 kips for our summation on each side of the point of maximum moment. And we end up with a C, the compression load in the concrete of 390 kips, controlled by the anchor strength. So next up on these 3 slides, I just went through the specification on how to calculate the width, which it ends up being 10 feet tributary to the center line of the adjacent beam. So the width of concrete is going to be defined by this effective width of 10 feet. So now what we can do is go in and calculate do a plastic analysis of the cross-section. And it's all going to be based on this, and I've got all the numbers coming up that I'll go through really quick, but of course the concrete, it's got to be based on a certain depth because we're partially composite. So we end up with a concrete compression of C sub C, and we have C sub F, which is the load in the flange at yield. This is going to be S sub Y equals 50 KSI here, and a C sub W, which is the load in the web above the plastic neutral axis. It's going to be based on 50 KSI. So now we get on the tension side of the plastic neutral axis down here, and we have a load in the flange in tension, 50 KSI for that one. The load in the web for tension, 50 KSI. But now what about the angle? Okay, it's going to be T sub A. That's going to be based on 36 KSI yield. Okay, so all I'm doing here is calculating the compression block depth of the concrete. It's based on the stud strength of 390. It ends up being almost an inch. And here I've got all of the loads calculated. C sub C in the concrete, the tension and compression forces in the flange, and the tension load of the angles. But once we get down here, we can't solve for a numerical number like we did for the rest. C sub W and P sub W. That's the loads in the web above and below the neutral axis. For that, we need to solve for X. So here's how I did it, just from basic statics. I just took the compression loads. They must equal the tension loads. Solve for X equals 3.44 inches. Now we can plug that in to get C sub W and T sub W. Next up, we calculate all of the dimensions on the cross-section. And the way I did it, I calculated the dimensions from the load to the plastic neutral axis. The example problem does it a little bit differently. I believe they may go to the top of the beam. I can't really remember how the example problem does it, but I wanted to show you a different way to do it and show you that either way can be an appropriate method. So now that we have the loads and the distances for each element in the cross section, we end up with a moment. Just multiply the load times distance for each element. We get a moment of 1,080 kip feet. So we multiply this by 0.9 to get the available moment is 972 kip feet. And that's greater than the required load of 844, or the factored load of 844, so we're in good shape there. Next up, I'm not going to go in detail on this. This is just the shear strength of the beam, and I just added it in for completeness. The same calc as in the example problem, with the exception of the live load is increased. You're just using the steel cross section, and the end of the beam is the location of the maximum moment, so we don't have reinforcement there anyway. We're going to solve for that in just a minute, the distance to the theoretical cutoff location. So we end up that our shear strength is good by a large margin. So the location of the theoretical cutoff point, we want to put as short of an angle in there as we can and still satisfy the requirements. And the reason is because obviously we want less weld on here for economical reasons, but also if we get a 45-foot long angle 2.5 by 2.5 in the field, it's not going to be easy to handle. These things are a lot more flexible than we usually think of steel being. So it's going to be pretty hard to handle a length that long, and I'm not sure, how available a 45-foot long angle would be anyway. So let's take a look at what we can do. We're going to take the value straight out of the example problem. Remember, this is without reinforcement. This is the moment strength of the beam before we added the angles, 769 kip feet. And then we're going to go to the manual, table 3-23, case 1, and solve for the moment as a function of x. And using the equations in the AIC manual, solve for x equals 15.5 feet. And that's where the moment is equal to our moment strength without any reinforcement. So that's where we can have our theoretical cutoff point on this beam. And me being a structural engineer, I'm usually pretty conservative, so I said, well, let's use a little bit smaller number than 15.5. Let's go down to 14 feet. And another thing to notice is that's a preliminary distance. Because now, the reason it's preliminary, it's good for strength, we know that. But as you'll see, I had to change it once we got to the deflection calculations. And, I'm not sure if the owner, we'll say that the owner wants to hold these same deflection limits as he had in the example problem. For all I know, this went from a dance floor to a warehouse. But we'll say he wants to go ahead and hold these limits. In the example problem, it was L over 360 was the first limit, and that's based on 100% of the live load straight out of the IBC. So that's going to be 1.5 inches based on the length of 45 feet. The second requirement was straight out of the AISC Design Guide for Serviceability. And what it says is use 50% of the design live load and limit your deflection to 1 inch. So we'll try and hold both of those deflection limits, and let's see what happens. Now the hard part of deflection calculations for composite beams is to figure out what the moment of inertia of the beam is. And if you go to the commentary, section I-3.2, there's two different simplified ways to do this. There are more in-depth ways, but it's not really generally designer friendly. The design example does it one way, and I selected another way just to kind of show you the different ways to do it. So the way I decided to do it is by this I effective that's in the commentary. It's 75% of I equivalent. All right, so I said that sounds easy enough. So what in the world is I equivalent? Well, the commentary also gives you an equation for that, and it's a little bit more complicated, but we pretty much know most of the things in here. I sub S is the moment of inertia of the steel section, the bare steel section without concrete. I sub TR is the transformed section moment of inertia, including concrete. We know what the stud strength is, sum of Q sub N, and C sub F is the compression load in the concrete, assuming full composite action. All right, so let's go in and calculate the transformed moment of inertia. And the first thing I did was calculate the modular ratio, 8.31. The transformed width is 14.4 inches based on that straight division of the 8.31 into the 10 feet. And plugged into one of the shape builder programs that are out there, and I came up with a transformed moment of inertia of 5,500 inches to the fourth. For the steel, all I did was wipe out the concrete part on top, and I kept the angles and ran the program again, came up with a I sub S of 1,170 inches to the fourth. And we know what the stud strength is, 390. And to find C sub F down here, we need to know what T, which is the yield strength of the beam, 860 that we calculated earlier, and C, which is the concrete compression strength that we calculated earlier. So take the minimum of T and C and come up with C sub F equals 860 kips. So now we know everything to plug into this equation in the commentary, and we end up with an I equivalent of 4,090 inches to the fourth. So I effective, you multiply by 0.75 to get 3,070. And now I used what we talked about at the very beginning of the lecture and did a finite element model based on the length, based on 3 elements on this beam, and used the actual length of reinforcement and my live load of 1.4 kips per foot. And you can see what I've done. I've used I sub 1 here, which I've called I sub 1 the reinforced section properties, and I sub 2 here at the beam ends, and ended up the deflection is no good. So at this point, assuming that we have to have the beam deflection less than that, well, the moment of inertia calculations aren't really very accurate. If you read the commentary in this to the specification in this section, you'll see that. So one option is to calculate the moment of inertia using a more rigorous approach. All right, and you can probably get enough out of it to get that deflection down to 1.5 possibly. Another thing is just increase your angle size. You can't really increase the horizontal dimension of the angle, or you won't have enough shelf dimension. But you can increase the vertical leg or the thickness of the angle to get a higher moment of inertia. Or you can do what I did and increase the length of reinforcement, L sub R. Now, what I ended up with, I would have really, actually in real life I would have never used this, because we ended up with a reinforcement length of 39 feet, which is going to be, in my opinion, it's a little bit hard to handle due to the flexibility of that angle that's that long. So using L sub R of 39, that gives us a D sub R of 3 feet, and our deflection is under the limit. So now we do the calculation for 50% of live load, and it turns out to be 0.73 inches, and that's less than 1, so we're good there. And the last thing we'll do is we need to design the welds at the end of reinforcement. And what we're talking about is beyond the theoretical cutoff point. We need to develop the welds over that distance. And if you go back to strengths of materials type or statics courses, then you'll know that the anchor force is MQ over I, like we talked about earlier. But the problem is that that's based on that's an elastic solution. And we just use plastic modulus to calculate our beam strength. So we really, that would be not be correct to use MQ over I here. So let's move on and see what we can do. What I did is I calculated the available strength of the angles using a P factor of 0.9 times the yield strength times the area of the angle. This is for one angle only. It's 56 kips. So we can develop the angle for the full yield strength, and it's only going to be 56 kips. So that's not too big. The strength of the weld is going to be just 1.39 for LRFD. That's the same as 0.928 for the ASD. Times the weld size in 16ths, that's 3, times the length of weld, which is, we've got 2 welds times 8 inches. So it's 66.7, and that's bigger than the yield strength of the angle. So we're good. And the last thing we'll check on this is the fracture strength of the web at the welds. We still have to check that. Remember, we have 2 welds, one on each side of the web, attaching the angles to the web. And you can go into the manual and get this equation. 6.19 times the weld size in 16ths divided by F sub U, which is 65 for the web. And we end up that we're at 0.286 is T-min, but that's less than the actual thickness of the web. So we're in good shape. You may want to check the angle for that same limit too. Okay, the last slide of the presentation is the final weld design. Here's the one we just calculated. Here's the theoretical cutoff point. We're going to go 8 inches beyond that. And we decided on a 3/16 fillet weld, 8 inches long. And I've got that dimension shown here too. And between the theoretical cutoff points, I just put a 3/16 weld with a 2 at 12, which means we have a 2-inch long weld, 12 inches center to center distance. Really quickly, one other way to show these welds is to, if you're showing a cross section instead of the side of the beam like I've got shown here, you can just eliminate. You can eliminate that weld and put a tail on this weld and just write in the symbol that I've got shown there and put in the tail 8 inches continuous at ends. Okay, Brent, I think that wraps it up.
All right, very good, Bo. Got a few more questions here, and we'll try to get to these with the very short amount of time we still have. Let me go back to slide 50 again. Bear with me a second. Again, looking at a reinforced column. Question came up again about the theoretical cutoff point. The comment in question is this: I understand how the cutoff point is calculated for a beam, but for an axially loaded column where there's no moment, how would the cutoff point be determined?
Okay, let's move it back to slide 49. All right, this is what I'm trying to do in this picture is show you on the previous slide. Let's go back to 48 here. We talked about adding this notional load, and all this notional load does is it, even though there's not a load on that column causing a bending moment, there's not an applied load on the column causing a bending moment, this notional load that we apply to this column has the effect of making it into a beam so that we have a moment and a shear along the length of that column. And the notional load is not actually, it's something that we apply just to account for the out of straightness, and which is going to give us an approximation of what the welds need to be designed for between the column and the reinforcement. So going back to slide 49, you'll apply this uniform load, even though it's not on there. It's just a notional load. And from that, you can get your moment and your shear.
Okay. I'm going to go to slide 89. All right, so in your design example, your wide flange beam is 50 KSI, and your reinforcement, your angles are 36 KSI. The question is this: can you use two different yield strengths and still have strain compatibility?
Well, the answer is yes, because we really don't need. The answer to the first part is yes, because we don't need strain compatibility in a plastic design of the cross section. We really don't have strain compatibility between the concrete and the beam either. But we just assume that the load at a certain point and calculate it based on the plastic properties. In other words, what's going to happen is the angle, they're going to have the same E, the same modulus of elasticity. So everything is going to deform elastically, and then we keep adding load, and eventually that angle is going to get to its yield strength, which is why we couldn't use MQ over I on this beam. The angle is going to get to its yield strength. It's going to yield, and it's going to go along that yield plateau at 36 KSI, and at the time, the beam is going to be at that location, 36 KSI also. But as you start adding more load to that beam, assuming perfectly plastic and no strain hardening, that angle is going to stay at 36 KSI while the beam goes up until it gets to 50 KSI.
Okay. We're running over on time now. There are a few other questions left. I'm going to coordinate with Bo on those last few questions and make sure we get responses out to you folks that didn't get your questions answered today.